Okay, we're going to work on resonance structures. And what a resonance structure is a single molecule that has more than one possible Lewis structure, where these different Lewis structures are both correct. And these resonance structures, these acceptable Lewis structures, typically are associated with when there are multiple bonds in the compound. So the carbonate ion, let's see if we can come up with something. The carbonate ion is CO3 negative 2. Nice, 2 pace. So that would be 4 valence electrons from carbon plus 2 is 6, and 3 more 6s. That's 4 6s, 24. 24 total valence electrons. And I'm going to use up 6 of them for bonding because I'm going to have 3 bonds between the carbon oxygens. So that's going to leave 18, the 18 valence electrons that I have to use. And I can't use any more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and I'm going to draw brackets around that thing on account of because that is the correct way to illustrate the Lewis structure of an ion. And I don't have an eraser. I don't have an eraser on the list. So as I proceed and start doing Lewis structures and doing octets and all, I'll have to scribble them. I can't erase them and make a double bond. But as you can see, there's 8 valence electrons, 8 valence electrons, 8 valence electrons, and 6 around the carbon. So we got to fix that. So I will take those two and make a double bond, and voila, the carbonate ion, and everyone's happy, relatively speaking. So a resonance structure is nothing more than saying, well, it would be certainly equivalent to put the double bond to one of the other oxygen atoms, which it is. And I'm not going to take the time to draw in all the lone pairs because it will take too long. Let's see, so I've got to go right there. So any one of those Lewis structures is acceptable for the carbonate ion. Not only are they all acceptable, they're all correct. And not only are they all correct, if there is a question that says draw the Lewis structure of the carbonate ion, it means all the resonance structures. So I've got a little deal right here that says, come on, evidence for the validity evidence for the validity of resonance structures is evident in bond length. So double bonds are shorter than single bonds, and triple bonds are shorter than double bonds. And so, and not only that, but those bond lengths are known. So it's known what the bond length is: a single bond between carbon and oxygen, and a double bond between carbon and oxygen, and a triple bond between carbon and oxygen. All those bond lengths are known. Yet when the bond lengths in the carbonate ion are measured, all the bonds are exactly the same length. And not only are they all exactly the same length, they're all a little bit longer than a carbon-oxygen double bond and a little bit shorter than a carbon-oxygen single bond. So what's literally happening is in the compound, in the ion, that double bond is resonating between all of the oxygen atoms. So it's literally trading places, click, 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 click. And so all of these resonance structures are present, and they're all contribute to the actual ion, and the bond lengths are an indication of that. So they're there and they're real, and yahoo. So with that in mind, the practice is draw some Lewis structure or draw some resonance structures. Oops, easy pace. So dinitrogen monoxide, I like this molecule on account of because students mess it up all the time. And I don't like it because they mess it up. I like it because it illustrates understanding of what you're supposed to do. And what you're supposed to do is put the least electronegative element in the middle, which is nitrogen, not oxygen. And I'll give that compound on a test, and 75% of the kids will put oxygen in the middle. And that's not correct. Easy pace. There, that's really supposed to be a nitrogen. So that's 5, 10, 16 valence electrons less 4 for bonding is 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 12. Oh, man. I thought I knew what I was doing, but I didn't. I was going to just draw the correct Lewis structure, but I can't do that. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 10, 12, 14, 16. We are golden. So there is not any real apparent Lewis structures right there because there's a double bond of that oxygen and a double bond of that to that oxygen and to that nitrogen from the central atom. But what if someone went like that? And by golly, 2, 4, 6, 8, 10, 12, 14, 16 total electrons. All octets are satisfied. Hallelujah. One each resonance structure. And then if you can put a triple bond between those two atoms, you can put a triple bond between those two. And then, oh man, that is a really handsome N. And then the lone pairs are all out on this terminal nitrogen, except that single lone pair, and voila, 3 Lewis structures for laughing gas, dinitrogen monoxide. And they are not all equivalent, by the way. Those I can give in a minute. I can show you that. In fact, I should show you that, I think, in a minute. Also, polar, yes, polar. That bad boy's polar. On account of because it's not symmetrical. There's an oxygen on that end and a nitrogen on that end, and indicate charge separation. So that one's slightly negative and that one's slightly positive, and that bond right there is totally nonpolar because it's between nitrogen and nitrogen. Slightly negative, slightly positive, nada, slightly negative, slightly positive, and nada. SF6. I just happen to know what that bad boy looks like. Are we supposed to say names or anything? Nope. I'm going to go fast. I'm not going to draw. So this is the structure with 3 lone pairs around each fluorine atom, and voila, we're done. And that is octahedral. It is the absolute picture of symmetry. So that is, although the bonds are all polar, the molecule itself is nonpolar. And there's the charge. There's charge separation in each bond, which I can show, but I'm not going to. I would just show the charge separation on the molecule. The nitrate ion That's going to be almost identical to the carbonate ion. In fact, it is going to be identical to the carbonate ion because it's got the same number of valence electrons. So it's going to look like that when we're all done. Like that right there. With a -1 charge. And I'm not going to take the time to draw the lone pairs in there, although do not make that mistake. If you leave the lone pairs off on the AP test, they'll hammer you for it. One resonance structure and another resonance structure. I'm not going to be able to fit all this in, so I'm just going to skip that one because I haven't got enough room to make it. Sorry. Ta-da. Resonance structures. 3 resonance structures for the nitrate ion, and they are all equivalent. No resonance structures over there. I forgot to say that. Sorry, bad teacher, no biscuit. No resonance structures on this one. There are no possible resonance structures. These are all equivalent. They all have an equal contribution to the creation of the ion. Yippee skippy. I'll tell you what I mean about that here in just a second. And it would be associated with the concept of formal charge. Formal charge, wow, that's a busy slide. Formal charge is the difference between the number of valence of electrons of each atom and the number of electrons the atom is associated with. I tend to call that the atom owns, and I'll show you what I mean by that. Formal charge assumes any shared electrons are equally shared between the two atoms. That's not a valid assumption, but just it's a bookkeeping thing, just to keep track of how many electrons in the molecule each atom quote unquote owns. It's used typically in 2 ways. Quit it. Way number 1 is select the most plausible resonance structure, and then you can determine where the most likely atom for a charge to reside on, and I can show you what that means as well. And you can use it to identify the best central atom. When I was telling you about the kids last year, and when they screwed the Lewis structure up on a given atom, that's where they messed it up right there. They didn't use formal charge to select the best central atom. So, to assign formal charge is total number of valence electrons minus lone pairs minus 1/2 the bonded electrons, which I'm sure is like, what in the name of common sense are you talking about, Pace? I will show you, I promise. The rules: minimize formal charge. If there is no formal charge in the resonance structure, it's a winner. But if there are formal charges, then the negative formal charge goes on the most electronegative element, and the positive charge goes on the most electropositive element, or the least electronegative. And the sum of the formal charges has to equal the charge on the species. So back there when we did the nitrate ion, the sum of the formal charges on the nitrogen and the 3 oxygen has to equal -1. If it's not an ion and it's a molecule, the sum of the formal charges has to equal 0. And I'll show you what I mean by all that noise here right along about now. Consider water. Water is in need of a pen. I'm going to draw it like I always draw it, which is not indicative of the way the molecule actually looks. So right there you go, water. And so I'm going to assign formal charge to each of the atoms in that molecule. And so to do that, you take the number of valence electrons and subtract from that all that. So you subtract from that the electrons that the hydrogen owns. So around the hydrogen right there is a bonding pair, and that's it. And so in that bonding pair, hydrogen has one of them and oxygen has one of them. So in this hydrogen right here, it has one valence electron and it owns one in that molecule. So the formal charge on hydrogen right there is zero. Hopefully, obviously, the formal charge on that hydrogen is zero. Now, oxygen, on the other hand, the lone pairs right there are not being shared with any other atoms around. And so the oxygen, quote unquote, owns them all. So it owns 1, 2, 3, 4 electrons from the lone pairs. And then it owns one from that bonding pair and one from that bonding pair. So if I were going to count the electrons that oxygen owns, I would go 1, 2, 3, 4, 5, 6. So oxygen has 6 valence electrons and it owns 6, and its formal charge is 0. So there are no formal charges on any of the atoms in there, and the sum of the formal charges is 0, and since that's a molecule, that's a wonderful thing. I wonder what Sol, or, oh yeah, this isn't even Sol, sadly, but I'm going to click on it anyway. Ready, fire, aim. What? Well, that didn't work. There we go.
In the previous video, we saw some steps for drawing dot structures. In this video, we're going to use those same steps to draw a few more dot structures, but we're also going to talk about how formal charge relates to dot structures, so we'll get back to this definition in a minute. For right now, let's draw a quick dot structure for the ammonium cation, so NH4+. The first thing you do is find the total number of valence electrons, and so to do that, you look at a periodic table and find nitrogen, which is in group 5. Therefore, nitrogen has 5 valence electrons. Right? Each hydrogen has 1, and we have 4 of them. So we have 5 plus 4 giving us 9 electrons. However, there's a +1 charge, meaning this is a cation, meaning we're going to lose an electron here. So instead of representing 9 in our dot structure, we're going to represent 8 electrons. And so let's go ahead and put the nitrogen at the center. Remember, we put the least electronegative atom at the center, except for hydrogen. So nitrogen is going to go in the center here, and we know it's going to have bonds to 4 hydrogens, so we go ahead and put in those hydrogens right here. And let's see how many valence electrons we've used up in our dot structure. 2, 4, 6, and 8. So that takes care of all 8 valence electrons that we were supposed to represent. So this is the dot structure. And I can go ahead and put some brackets around it here, and also a +1 charge to indicate that this is an ion. And so that's the dot structure for the ammonium cation here. Let's see if we can assign formal charges to the nitrogen and the hydrogen. So I'm going to go ahead and redraw our dot structure here. And I'm also going to draw in the electrons, right? We know that each of those covalent bonds consists of 2 electrons. Let me go ahead and put in those 2 electrons right here. And if I wanted to find a formal charge for, let's say, the central nitrogen, right, what I would do is think about the number of valence electrons in the free atom. So if you had a nitrogen all by itself, right, you look at the periodic table, it's in group 5, and so therefore we're talking about 5 valence electrons in the free atom for nitrogen. From that number, we're going to subtract the number of valence electrons in the bonded atom. And the way to approach that is to look at your dot structure here and think about those 2 electrons in those covalent bonds, right? One of them we're going to assign to the hydrogen, and one of them we're going to assign to the nitrogen. And so we go around, we do that for each one of our covalent bonds like that. And so now we can see that nitrogen is surrounded by 4 valence electrons in the bonded atom. So let me go ahead and write that. So it's 5 minus 4. And so 5 minus 4 is, of course, plus 1. So we have a plus 1 formal charge on the nitrogen. So this nitrogen has a plus 1 formal charge. Now let's do it for hydrogen here. So hydrogen's in group 1 on the periodic table. So let me just point this out. This is for nitrogen. And then for hydrogen, right, it's in group 1, so 1 valence electron in the free atom, and from that we're going to subtract the number of valence electrons in the bonded atom. So if we look here, right, we assigned 1 valence electron here to each hydrogen, so therefore it's just 1 minus 1, or 0. So there's 0 formal charge for all of the hydrogens in the ammonium cation. And so that's how to assign formal charges. Let's see how that applies to actually affecting our final dot structure. And an example of that would be something like sulfuric acid here. So the first step, of course, is to calculate the total number of valence electrons we need to worry about in our dot structure. So once again, each hydrogen is 1, and I have 2 of them. Sulfur is in group 6 on the periodic table, so therefore it has 6 valence electrons. Oxygen is also in group 6, and so we have 6, and we have 4 of them right here. So 6 times 4 is 24, right? So we have 24 plus 6 is 30, plus 2 is 32. So we need to worry about 32 valence electrons in our dot structure for sulfuric acid. All right, next thing we need to do is choose the central atom. And once again, you ignore hydrogen, so it's between sulfur and oxygen. And if you look at a periodic table, you will see that oxygen is higher in group 6 than sulfur is. Therefore, oxygen is more electronegative. And so therefore, we're going to put sulfur at the center, right? So we're going to put sulfur right here. And once again, look at the rules from the previous video if that didn't make quite sense to you here. So we have sulfur attached to 4 oxygens. I'm going to go ahead and put my 4 oxygens in there like that. And then I have 2 hydrogens. And by experience, you're talking about an acid here. You're going to put your hydrogens on oxygens. And so we're going to go ahead and put our hydrogens here. And let's see how many valence electrons we've used up drawing this skeleton here. So we have 2, 4, 6, 8, 10, and 12. So we've used up 12 valence electrons, so 32 minus 12 gives us 20 valence electrons left to worry about. And so remember, the next step is to assign some of those leftover electrons to some of the terminal atoms. But again, we're not going to assign those electrons to hydrogen because hydrogen is already surrounded by 2 electrons. And so we're going to try to assign some electrons to oxygen, and oxygen is going to follow the octet rule. So let's examine, let's say, the top oxygen here, and we can see the top oxygen is surrounded by 2 electrons already right there in green. And so if we're going to give it an octet, it needs 6 more. So we have 1, 2, 3, 4, 5, 6. Same thing for this oxygen down here. It needs an octet, so we go ahead and give it 6 more electrons like that. Right? So we also have these other oxygens over here to worry about. So let me go ahead and use green again. So let's say this oxygen over here on the left, the one bonded to this hydrogen, here's 2 electrons, and here's another 2 for 4. So for that oxygen to have an octet, it needs 4 more. So that means we're going to put 2 lone pairs of electrons on this oxygen, and then we're going to do the same thing for this oxygen as well. So let's see, how many electrons did we just represent there? Well, we had 6 on the top oxygen, 6 on the bottom oxygen. That's 12. And then we had 4 on the left and 4 more on the right. So that's 8. So 12 plus 8 is 20. So we've now represented all of the valence electrons that we needed to show. And let's think about this as possibly being the final dot structure, right? So we have an octet around sulfur, we have an octet around oxygen, and hydrogen's fine. So you might think that we are done here. However, let's go ahead and assign some formal charges, and let's see what that does. So let me go ahead and draw in some electrons here. So we know that each bond consists of 2 electrons. I'm going to go ahead and make them red here, like that. And let's assign a formal charge to the top oxygen here. All right, so this top oxygen right? I'm going to, in the bond between oxygen and sulfur, I'm going to give one of the electrons to oxygen and one of the electrons to the sulfur, right? And so I can see that oxygen is being surrounded by 7 electrons. In the free atom, right, we would expect oxygen to have 6 valence electrons. 6 minus 7 in this case gives us a formal charge of -1. And so this top oxygen has a formal charge of -1. It's the same situation for this bottom oxygen here, so that one has a formal charge of -1 as well. Let's look at the sulfur. All right, so if we examine the sulfur here, and we know, right, sulfur's in group 6 on the periodic table, so normally 6 electrons, 6 valence electrons for the free atom. And in this bonding situation, right, let's go ahead, we know this one oxygen goes, this one electron, I should say, goes to sulfur, and then in this bond between oxygen and sulfur, sulfur is going to get 1 electron, and so on all the way around here. So sulfur is surrounded by 4 electrons in the bonded atom here, and so it's 6 minus 4, which is a formal charge of +2. So this dot structure might look like we're done, but we have a lot of formal charges, right? We have -1, +2, and -1. And usually molecules like to minimize the formal charge. And so if there's any way to get this formal charge as close to 0 as possible, that would be the preferred dot structure. And so let's go ahead and redraw this really quickly, and let's see if we can move some electrons around to minimize our formal charges. Now we can't add any more electrons because we've already represented all 32 valence electrons that we were supposed to. So the only thing that we can do is to share some more electrons. And so if I took 2 electrons from this top oxygen here, so if I took these 2 electrons and I moved them into here, and if I took these 2 electrons right here and I moved them into here to form double bonds, let's go ahead and look and see what our dot structure would look like and assign some formal charges. So now I would have sulfur double bonded to this top oxygen and double bonded to this bottom oxygen. Top oxygen has only 2 lone pairs of electrons around it, same thing for this bottom oxygen, and then these oxygens are the same with the OH on the left, and then we have the OH on the right here. Okay, so now let's look at our formal charges. So we'll put in our electrons, so let's go ahead and do that. And once again, we're going to do the same thing that we did before. So assigning formal charges, we'll start with the top oxygen here. So the top oxygen, right, 6 valence electrons in the free atom, and then if I go like that, you can see there are 6 here. So 6 minus 6 gives us a formal charge of 0. So the top oxygen is 0 now. Same thing with this bottom oxygen. This one's 0. Let's look at the sulfur now, right? So normally we're talking about 6 for the sulfur, and let's see how many valence electrons are around the bonded atom here. So we do the same assigning of electrons that we've done before, and so now we can see that that sulfur is surrounded by 6. So we would go 6 minus 6 gives us a formal charge of 0. And if you assign a formal charge to one of these other oxygens, so let's go ahead and do that really quickly. So one of these other oxygens right here, so I'm doing the oxygen on the right. Okay, so let's see how many valence electrons are surrounding this atom. So we have a total of 6 as well. So 6 minus 6 is a formal charge of 0. So this dot structure actually gives us formal charges of 0 for everything, and so this would be the preferred one. And let's finally talk about octets, right? So we know that hydrogen is happy surrounded by 2 electrons. We know that oxygen is happy with an octet, and so you can see that all of these oxygens have an octet. Sulfur, in this case, is not surrounded by an octet. It has an expanded outer shell. Right? It's okay for sulfur to have an expanded valence shell because it's in the 3rd period on the periodic table, and so we talked about why that's okay in the previous video. And so this is just one more thing to think of when you're drawing dot structures. Sometimes formal charge will affect the final structure of your molecule or ion.
And there, by golly, you have it. Sure enough, the initial Lewis structure for sulfuric acid looked like it's like, oh yeah, buddy, we have got it, we're done, happy as a clam. But no, needed to expand the octet on that sulfur atom to get formal charges of 0 on all the atoms, and by golly, there it is. And so sometimes you have expanded octets when you don't really think you need them, but the formal charges leads you to that idea. Thiocyanate ion. So the pen. The thiocyanate ion is SCN minus. I'm not exactly sure which one of those has the lowest electronegativity, sulfur or carbon, but I know which one I'm going to put in the middle. So I'm going to put carbon, nitrogen, sulfur, -1. So that's 5, 6, 10, 16 total. Valence electrons minus 4 is 12. That is going to be, we had that exact same thing on the dinitrogen monoxide. It'll look like that. That way I don't have to erase any valence, any lone pairs. 2, 4, 6, 8, 10, 12, 14, 16. And we had 16 total valence electrons from the get-go, so we are golden. So let's check for formal charges. 1, 2, 3, 4, 5, 6. Bobby, shut up. Sorry about that. Bobby's protecting me. So sulfur has 6 valence electrons. It owns 6 in the molecule, so formal charge of 0. Carbon has 4 valence electrons, and it owns 1, 2, 3, 4 in that particular configuration, so the formal charge is 0 on that one. Nitrogen has 5 valence electrons, and it owns 1, 2, 3, 4, 5, 6. So there is a charge of -1 on that nitrogen atom, and there you go. So that is 0 plus 0 plus -1 is -1. We're all groovy, other than, I don't know that we're not groovy. But we could draw a resonance structure where we had a sulfur atom with a triple bond to it and a single bond to the nitrogen atom. Or we could do a carbon atom with a triple bond to the nitrogen atom and a single bond, yikes, to the sulfur. Man, I wish I could erase. Sorry about that. And I'm going to draw in the lone pairs because they kind of need them to assign formal charge. So the sulfur atom right there it has 6 valence electrons, and it owns 1, 2, 3, 4, 5. So the formal charge on that sulfur is +1, 1, 2, 3, 4. 4 minus 4, the carbon is 0 again, and the nitrogen is 1, 2, 3, 4, 5, 6, 7. The formal charge on that nitrogen atom is -2. So 1 plus 0 is 0, minus 2 is -1. We all add up, it's all good. So this one, nitrogen has 5 valence electrons, and it owns 1, 2, 3, 4, 5. Formal charge is 0 again. 1, 2, 3, 4, 1, 2, 3, 4. Formal charge is 0. This one will have a formal charge of 1, 2, 3, 4, 5, 6, 7. It owns 7, but has 6 valence electrons, a negative charge of -1. So there you go. And so then we would be on the hook to determine which one of those is the preferred Lewis structure, and it's not that one. That one has more formal charges. It's got formal charge of +1, formal charge of -2. We're minimizing formal charges. We're going to throw that one out. We would throw that one out anyway on account of because there's a -2 charge on nitrogen. Nitrogen's electronegative, but -2 charge on it, not so great. So then we've got the choice between these two, where there is a -1 charge on nitrogen or a -1 charge on sulfur. And nitrogen has a higher electronegativity than sulfur, so I would say that one is the preferred resonance structure on account of because the negative charge is on the formal charge of -1 is on that nitrogen atom with a higher electronegativity than the formal charge of -1 on that sulfur atom right there. Whew. And yes, this one's the preferred one, but this one and this one probably all exist to some extent in the real ion. It's just that this would be the dominant one. And there you go. There's way more to this. Well, that is it, but there's way more practice to it, and there are some chlorine oxygen compounds that have some whacked out Lewis structures when you get doing formal charges. But we'll leave that to a later date, and there you go. Take care then. Bye-bye now.